We are now going to talk about how we can solve allocation problems using something known as the Hungarian algorithm. So what is the Hungarian algorithm? The Hungarian algorithm uses cost matrices to find the optimum allocation of vertices in one set to vertices in the other set. That is, the allocation with the overall minimum cost. So the Hungarian algorithm is used to show the connections between two different aspects of a task, e.g. people allocated to tasks, stock allocated to stores, study time allocated to subjects. We are usually concerned with minimizing cost and time. However, watch out for trick questions. Okay, let's go through this example here, which really holds our hand and really does all the working for us. So we're just going to take our time to really soak it all in. All right, so for example, 4 students have gotten together to design and construct their outfits for the end of year school social. The graph below shows the tasks and times taken to complete by each student in hours. So for instance here, we have Vanita, and Vanita takes 8 hours to do designing, 10 hours to do purchasing, 6 hours to do cutting out fabric, and 5 hours to do sewing. Stan takes 9 for designing, 8 for purchasing, 7 for cutting, and 10 for sewing, and so on. So here it says Vanita, Stan, Ebony, and Philip only want to perform one task each and get the outfits made in the shortest time possible. How long will the project take? So as soon as you have got a problem in which you want to assign one person per task, and you want to talk about the shortest time possible, as soon as you've got this, you know that you're dealing with what? You're dealing with the Hungarian algorithm. You've got on your hands an allocation problem. So these are the key words you've got to be looking out for. Shortest time, everyone gets a task. That's what you're keeping your eye out for. So how are we going to use our Hungarian algorithm to solve this problem? The first thing that we're going to do is we're going to take our bipartite graph and put it into a cost matrix. So this is step 1. Represent the times taken in a matrix. So here it is right here. And as you can see, for Vanita takes 8 hours for designing, 10 for purchasing, 6 for cutting, and 5 for sewing. And sure enough, Vanita has 8 for designing, 10 for purchasing, 6 for cutting, and 5 for sewing. So all I've done is I've taken this 8, 10, 6, and 5 and put it here, 8, 10, 6, and 5, and done the same for the rest. Let's now move on to step 2. Okay, so what's step 2? Step 2 is row reduction. So that is subtract the smallest value from each row. So find the smallest number in the row and subtract it from all the other numbers in that row. So for instance, in the Vanita row here, we have the smallest number of 5. So that means we're going to subtract 5 from every number in this row. 8 minus 5 is 3. 10 minus 5 is 5. 6 minus 5 is 1. 5 minus 5 is 0. We go to our next row, where the smallest number is 7. So now we're going to subtract 7 from every number in this row. 9 minus 7 is 2. 8 minus 7 is 1. 7 minus 7 is 0. 10 minus 7 is 3. And then so on. The next smallest number is 4, so we subtract 4 from every number in this row. Then this is 3, so we subtract 3 from every number in this row. And we end up with a new matrix here. That now takes us to step 3. Step 3 is column reduction, when you subtract the smallest value from each column. So now it says find the smallest number in the column and subtract it from the other numbers in that column. So if we look here, we're now looking at the columns and try to identify the smallest number. Well, the smallest number of this column will be 0. So that means I need to subtract 0 from every number in this column. Well, 3 minus 0 is 3. 2 minus 0 is 2. 0 minus 0 is 0. 2 minus 0 is 2. So what you should notice is that if you have a 0 in your column, we actually don't change that column. For our next one, the smallest number is going to be 1. So that means we're going to subtract 1 from every number in this column. 5 minus 1 is 4. 1 minus 1 is 0. 5 minus 1 is 4. 7 minus 1 is 6. Now for the next 2 columns, we have zeros in there. And as soon as you have zeros in your columns, you know that you're just going to be subtracting 0 from this column and 0 from that column, so nothing will change. And here it says, in D, subtract 0, in P, subtract 1, in C, subtract 0, and in S, subtract 0. We now come to step 4. Step 4 is cross out along rows and columns all of the zeros so that the minimal numbers are lost. So each 0 represents a possible match of the persons to a task. So what we want to do now is we want to draw lines such that they cross out all the zeros in the matrix. So as you can see, I can draw through there. I can draw through there, and I can draw through there. And you want to try to do this with the minimal amount of lines possible. Now, this is the important part. You should underline this statement right here. Do you see how it has two asterisks next to it? That means it's very important. It says the number of lines has to be equal to the number of jobs to be done. So the fact that I have 1, 2, 3, 4 tasks here means therefore I must have 4 lines. But at the moment, I don't have 4 lines. At the moment, I have 1, 2, 3 lines. So that is a problem. So here it says, in this case, only 3 lines are needed. So we need to keep working before we can allocate tasks. So the fact that I only needed 3 lines to cross out all the zeros means I've still got more steps to do. If I had managed to have 4 lines to cross out the zeros, then I would be done here. And also take note of the fact that you need to use minimal lines possible. So you can't just like draw 4 lines down each one. You couldn't just go 1, 2, 3, 4. Look, there's 4 lines. No, that doesn't work. You need to use as minimal lines as possible. So the fact that I could draw a line through here and get both of those zeros, and a line through there and get both of those zeros. So that's important. And that says here, so that minimal numbers are lost. Minimal numbers are lost. So you want to do it in such a way that you're not losing too many numbers. Okay, step 5. And remember, we're doing step 5 because we didn't get 4 lines. So step 5 says subtract the smallest uncovered number from all other uncovered numbers. Okay, so my uncovered numbers are 4 and 1 and 4, 4, 6, and 4. So my smallest number there is going to be 1. So that means I want to subtract this 1 from all the other uncovered numbers. So 4 minus 1 is 3. 1 minus 1 is 0. 4 minus 1 is 3. 4 minus 1 is 3. 6 minus 1 is 5. 4 minus 1 is 3. And you can see by doing this, we now have another 0. So now, step 6, redraw the lines along the rows and columns to cross out the zeros. So now this time, I need 4 lines for my I need 4 lines to cross out all my zeros here. So that means that I'm done. Now, there are still more steps, but I'm done this part. So step 7 says, repeat step 6 until the number of lines matches the number of tasks to allocate. So we are done here. So step 6, we have 4 lines and 4 tasks. So that means we're finished. We don't have to go back to another step to keep doing this. We are done here. So now it says step 8. Allocate people to tasks using the zeros. Start with the combination that only has one possible allocation. All right. So now we've got this right here. This right here is what we've got. So remember, we're just taking this one right here. We aren't looking at the lines anymore. We got rid of the lines. And now it looks like this. Now you want to try to allocate people to tasks. And the way that you're going to do that is begin with people who are only allocated 1 tasks. And you're going to be looking at the zeros to figure this out. So do you see here how P has only a 0 in the S? So that must mean that Philip is doing sewing. Philip is doing sewing. Now, if Philip is doing sewing, that means Vanita can't do sewing. That means Vanita must be doing C. So I'll come to Vanita. Vanita must be doing cutting. That's the only other option that she's got. I'll grab another color. Let's go this color. Next, I've got, now E has only one option, and that one option is D. E only has D as an option. So that means Ebony has to do designing. And then I need to grab another color again. It's going to have to be an ugly color. It's going to have to be orange. Now, if Vanita is doing cutting, that means that S can't do cutting. S must be doing P because cutting is already taken by Vanita. So S to P. All right, Stan to purchasing. And just like that, we have allocated everyone their task. So Stan is doing purchasing. So step 9 now is calculate the time/cost needed to complete the project. So in this instance right here, what you're going to do is really come back to the original cost matrix and read it off. So if I get my colors back here, do you see how Vanita C0? So Vanita was this one, that one. So that's where I'm getting that 6 from. And then I'll grab color again. As you can see, Stan was a 0p. So Stan, go to the same position, that's 8p. And that's why I've got an 8 there. Then we keep on going. Ebony, sorry, was 0d. Ebony, there, D. So that's 4. That's why there's a 4 there. So hopefully you can pick up the pattern here. Let's go one more time. We've got P0S, P3S. So as you can see, they're always in the same position as the original cost matrix. And this cost matrix isn't actually in your notes. I've just kind of copied this back in there. So that's that 3 there. 6 plus 8 plus 4 plus 3 is 21. So therefore, you need 21 hours is needed to complete the task as efficiently as possible. Also note, sometimes there are 2 possible solutions to an allocation problem that yield the same minimal time/cost. So guys, that is the Hungarian algorithm. We have gone through it all just there, and hopefully you found that helpful. We'll now continue on.